In a breakthrough development, researchers from Carnegie Mellon University and Meta AI have finally unveiled their new approach to robot learning, known as Vision Robotics Bridge or VRB, which is an innovative AI model that leverages the concept of affordances to accelerate the learning process for robots. But before we reveal the 5 key applications of this technology in the real world and the transformations it will enable, first you need to understand the importance of affordances in robotics. This concept was originally coined by psychologist James J. Gibson, where affordances are defined as the sum of contact points and post-contact trajectories in the context of robotics. Because the VRB model is trained on video data, it learns to identify objects and their associated actions, as well as potential movement patterns after an object is grasped. The VRB model is a significant leap forward in the field of robotics, offering a solution to the chicken and egg problem of robot training data. Comprehensive robot training data would require many robots performing actions in the real world, but they would need to be trained on them beforehand. Video training is seen as a possible solution, as AI models could learn how humans interact with their environment from video data and then transfer these skills to robots. In practical terms, the VRB model learns that a fridge is opened by pulling the handle and in which direction a person pulls it. In the case of a drawer, it recognizes the handle and learns the only correct direction of movement to open the drawer. This ability to understand and predict human interactions with the environment is a significant step forward in the field of robotics. The VRB model has been extensively tested in real-world environments, proving its effectiveness over more than 200 hours of experiments. The researchers demonstrated that VRB is far superior to previous approaches, showing its compatibility with 4 different learning paradigms and its applicability in more than 10 different tasks using 2 different robot platforms. Because of this, the team is optimistic about the future of the VRB model, and they plan to apply their method to more complex multi-step tasks, as well as incorporate physical concepts like force and tactile information, all to investigate the visual representations learned from the new model. Overall, the introduction of the VRB model is a testament to the imminent potential of AI in revolutionizing the field of robotics. By learning from human interactions, robots can gain a deeper understanding of their environment, leading to more efficient and effective performance. The Vision Robotics Bridge model, with its innovative approach to robot learning, holds immense potential to revolutionize the field of robotics. By enabling robots to understand and interact with their environment in a more nuanced and effective manner, it opens up a plethora of possibilities for the application of robotics in various sectors. Of all impacts of this new tech, the first and most significant impact of the VRB model could be seen in the realm of industrial automation. Robots equipped with the ability to understand affordances could drastically improve efficiency in manufacturing processes, because they can now adapt to changes in the production line in real time, handle a wider variety of tasks, and reduce the need for human intervention. This could lead to increased productivity, reduced costs, and improved safety in industries. The second impact is in the healthcare sector, where the VRB model could revolutionize patient care. Robots could learn to interact with medical equipment and patients, assisting in tasks ranging from routine checkups to complex surgical procedures. They could also provide support in rehabilitation, helping patients regain their motor skills by understanding and responding to their movements. The third potential of the VRB model extends to the realm of personal assistance, where robots could learn to perform household chores by observing human behavior, understanding the environment, and predicting the likely actions. This could lead to the development of more sophisticated and helpful domestic robots, making daily life easier for individuals, particularly for the elderly and those with disabilities. The fourth potential use case for the VRB model would be to significantly enhance the capabilities of service robots in sectors like hospitality and retail. By understanding human interactions and the environment, robots could provide more personalized and efficient service, improving the customer experience. The fifth potential use case of the VRB model could be to play a crucial role in disaster response, where robots equipped with it could better understand and navigate complex environments, assisting in search and rescue operations, reaching areas that are inaccessible or dangerous for humans. By enabling robots to learn from human interactions and understand their environment, the VRB model opens up a world of possibilities for the application of robotics in various sectors. As this technology continues to evolve, we can expect to see a profound transformation in the way robots interact with the world, bringing us closer to a future where machines are an integral part of our everyday lives. In fact, this might be one of the key technological breakthroughs that provides general humanoid robots the ability to interact with any environment just as a human would. But that's just the tip of the iceberg in terms of AI breakthroughs, because in a seemingly impossible AI project called Seeing the World Through Your Eyes, a team of researchers at the University of Maryland had discovered a novel way to reconstruct 3D scenes using only the reflections in the human eye, which the researchers argue is an underexplored source of information about our surroundings that could be applied to a series of interesting scenarios. To accomplish this feat, the researchers have developed this method using neural radiance fields to reconstruct a 3D scene from an eye reflection. While this might sound straightforward, it's a complex process that involves several factors, including accurately determining the direction of gaze and distinguishing reflections from patterns in the iris. To calculate the outside world, the team uses the geometry of the cornea, which is fairly uniform in healthy adults. Based on the size of the cornea in an image, they can estimate the position and orientation of the eye. An important aspect of this process is optimizing the detection of the cornea's position, which is used to refine the initial position estimate for each image. This technique has proven to be critical to the robustness of the method. To separate the reflection of the outside world from the iris pattern, the team used a modified training framework from Nerf Studio. They had Nerf learn both the reflected 3D scene and the iris pattern, and simultaneously trained the system to separate the two elements. For iris detection, the system was given the general radially symmetric shape as a default, at the assumption that the reflection changes from different perspectives, but the texture of the iris remains the same. While typical Nerf reconstructions require multiple camera views of the object being reconstructed, the researchers simply moved the person through the camera's field of view. The reflections in the eye, which change with even minimal movement, provided the different perspectives needed to reconstruct the 3D scene, even though only one camera saw the person. To validate their method, the team used synthetic eye images rendered with Blender and real photographs of a person moving in the camera's field of view. Despite challenges such as inaccuracies in locating the cornea and estimating its geometry, at the inherently low resolution of the images, their method showed promise. In tests with synthetic eye models, the team was able to perform full scene reconstructions using only eye reflections. However, the tests were conducted only in the laboratory. In reality, many other factors are at play, and the assumptions made in the paper, such as about the texture of the iris, may be too simplistic. Brighter iris textures or situations involving strong eye rotation could pose additional challenges, the researchers write. The team hopes the work will stimulate further research into how unexpected random visual signals can be used to reveal information about the surrounding world. This innovative approach could open up new avenues for understanding human perception and developing advanced technologies for visual reconstruction. The potential applications of this research are vast, including entertainment and virtual reality, where it could offer a more immersive and personalized user experience by adapting the virtual environment based on the reflections in the user's eyes. Furthermore, in the field of social robotics and human-computer interaction, this technology could enable machines to better understand human perspectives and respond more intuitively to human needs. As we continue to explore and refine this technology, the way we interact with our environment and the machines around us could be fundamentally transformed. As we continue to push the boundaries of what's possible with AI and computer vision, the world as we see it is set to change in ways we can barely imagine.